Welcome again to our discussions of the homework in the Titelbaum book. We're up to chapter 4 today. 4 is pretty much preparatory for chapters 5 and 6, and there will be more on the take-home final from those chapters. So it's important to understand what's going on in chapter 4, but none of it's going to show up on the take-home final. All right, so problem 4.1 is just some number crunching. The easiest thing to do is to use Bayes' theorem on these. You are told the relevant numbers for applying Bayes' theorem, and then you just plug them in and you generate a value by doing so. So we are told something about dropping 2 cannonballs. He's 95% confident that they'll land within 1/10 of a second of each other. If the quantities are dependent, he's 80% confident that the balls won't land within 1/10 of a second of each other. And then we're asked to do some calculations. So before performing the experiment, Galileo is 0.3 confident that mass and gravitational acceleration are independent. How confident is he that the cannonballs will land within 1/10 of a second of each other? So begin by using the ratio formula on the right side of Bayes' theorem, using I and L for H and E. So I meant the left side. Let me fix that. So let's begin by using the ratio formula on the left side of Bayes' theorem, using I and L in place of H and E, seeking the probability of L. The left side is the probability of I and L divided by the probability of L, which is 0.3 times 0.95 over L. The values on the right side are 0.95 times 0.3 over 0.95 times 0.3 plus 0.2 times 0.7. We thus get that 0.285 over the probability of L is 0.953. Solve for the probability of L and you get 0.299. Just some simple number crunching in Bayes' theorem. After Galileo conditionalizes on the evidence that the cannonballs did land within 1/10 of a second, how confident is he in each hypothesis? Well, the new unconditional probability is the old conditional probability, which we saw above, is 0.953, leaving 0.047 as the probability of not L. All right, more general questions, not simple number crunching. Prove that conditionalization retains certainties. In other words, prove that if your initial credence for H is 1 and a later credence is generated from it by conditionalization, then the later credence for H has to be 1 as well. So you begin by assuming that you're certain of H. Consider then learning something else, E, or something, E. The probability of H on E is by Bayes' theorem, that thing. Now, instead of putting in the probability of H in the numerator, I put in 1 because we're assuming you're certain of H. And same thing in the denominator. And if the probability of H is 1, the probability of not H is 0. So this second number is going to be 0. Since the probability of the denial of H is 0, this fraction reduces to the probability of E given H times 1 over the probability of E. That's supposed to be, that's another typo. So assume you're certain of H, and then we're going to learn E and update. So the conditional probability, the new unconditional probability will be the old conditional probability of H on E, which is by Bayes' theorem, this formula. Now, since the probability, I put in the 1s for the probability of H, and since the probability of not H would then be 0, this fraction reduces to probability of E given H times 1 over the probability of E given H times 1, which reduces, of course, to 1 over 1, which is 1. So for any E whatsoever, updating to a new unconditional probability by respecting conditional probabilities will leave certainties unchanged. Problem 4.3, prove that conditionalization is cumulative. That is, prove that for any 3 credences where I is before J, which is before K, if you update at time j on the basis of conditional credences from I, and then you update at k on conditional credences at time j, then you will be updating at k on the basis of conjunctive credences. So you learn E between I and j, and then you learn E prime between j and k, which is the same thing as updating to k straight from I based on the conjunctive evidence, E and E prime. So we assume that conditions 1 and 2 are true, and then remind ourselves that updating by conditionalization on E is really updating on the basis of E plus K, where K is background knowledge or certainties. So when we update on E prime, we're really updating on that plus background knowledge, which includes E already. So no matter what proposition we are doing the update on, both E and E prime will be included in the old conditional probability given assumptions 1 and 2. Provide an example in which an agent conditionalizes on new evidence, yet her credence in a proposition compatible with the evidence decreases. That is, provide an example in which H and E are consistent, yet the later credence is lower than the earlier when E is learned between T1 and T2. It almost looks like too easy a problem, because obviously you should be able to acquire negative evidence that's consistent with the hypothesis you're trying to test. So it shouldn't be that hard. So here's one. Let H be the claim that 2 throws of a die sum to 7. Then you learn that the first throw is a 1. You are now less confident than you were before that the sum will be 7. Prove that when an agent conditionalizes on new evidence, her credence in a proposition that entails the evidence can't decrease. That is, when H entails E, it must be the case that the later credence is at least as high as the earlier credence when E is what is learned between the 2 times. Okay, the probability of E given H has to be 1 if the entailment claim holds. Moreover, when E is learned, it comes to have a probability of 1. Now, the maximal value for the denominator is 1, since the maximal value for the denominator is 1. Now, what denominator am I talking about? I'm talking about replacing E given H, or H given E, and let's talk about H given E. H given E by the ratio formula is H and E over E. So the maximal value for the denominator is 1. So the probability of H given E has as its maximal value the probability of H itself. All right, let me write that out. So by the ratio formula, the probability of H given E is H and E over E. The conjunction at the top is H times E given H. The probability of E given H is 1. So what we end up with for the conditional probability in this special case is the probability of H over the probability of E. Now the maximal value for the denominator is 1. And that's what E comes to have when you learn it. If E is anything less than 1, you're doing the same thing as multiplying H by some number larger than 1, so H will grow. It could only, as its minimal value, it could only stay the same, which it does when the probability of E is 0. So after updating by conditionalization upon learning E, the new probability can't be lower than the initial unconditional probability of H. All right, prove that as long as the 2 probabilities are non-extreme, conditionalizing on E increases the agent's credence in H when H models E, or models is a synonym here for entails. Now, as we just saw in answering B, the probability of H given E has H as its minimal value when and only when the probability of E in the denominator is 1. So if we assume that the probability is strictly less than 1, the conditional credence will be larger than the unconditional credence of H, because you'll be multiplying the probability of H times the number larger than 1. Moreover, if neither have a probability of 0, the fraction will be defined and will be strictly larger than the unconditional probability in the numerator. So either way, the new probability has to be larger than the old given non-extreme probabilities for H and E. 4.5, the base rate fallacy is a very important one. It's an artificial example in some ways because it has you being told by your doctor that you're supposed to get some diagnostic test for a disease. But in the usual case, it gives you the frequency of the disease in the population, and you're supposed to treat that as the unconditional prior probability of the hypothesis. In the usual case, when a doctor tells you that a diagnostic test would be appropriate for you, they're relying on more information than merely the base rate of the disease in the population at large. About the only time that base rate frequency in the population at large could be the prior probability would be in public health situations where everybody is being tested for a certain thing. I believe they do this with mammograms in Great Britain, for example. Every woman takes the test. You're not advised by your doctor whether or not to take the test. So in some public health circumstances, the base rate fallacy can be relevant. But in any case, the base rate fallacy is supposed to illustrate that getting a positive result for a disease on a diagnostic test doesn't actually raise the probability that much. So you need to be able to solve this problem. In order to solve it, you have to be able to convert between odds and probabilities. And then it's just plugging in numbers. So that's a pretty boring project. You can figure out the credence for the disease is 0.001. The credence for not having the disease initially is 0.999. You're told the false positive and false negative rates. This is false positive. The test shows positive even though you don't have the disease 10% of the time. And the other credence is the probability of getting a positive test if you have the disease, and that's 0.9. These numbers you just plug into Bayes' theorem. This is the calculation that you got for the first test. Then you use the numbers generated down here to plug back into Bayes' equation again, and once you do it a second time, the probability jumps from 0.0, let's see, that would be what, 0.009, all the way up to 0.075, which is a huge increase, but not even close to making it more likely than not that you have the disease. So how many consecutive tests do you need to run, assuming that they're all independent, each is independent of the prior test, conditional on both having the disease and not having the disease? How many times do you have to run the test? Well, if you plug it in a third time, the probability jumps to 0.2, so by the fourth test, the disease would be more likely than not. Does this shed any light on why patients diagnosed with rare diseases are often advised to seek a second opinion? And the answer is, well, of course. Seeking a second opinion, maybe the second doctor will have you run the same test and the results will be independent of the first test. You could also run the same test with the original doctor. There's no reason why you have to go to the second doctor to get the test run again. But perhaps the advice should be to seek several repeats of the test. Okay, 4.6, well, a bit more number crunching here, but a little bit of logical analysis needed to set up the case. So your friend Jones is a gambler. He even gambles about whether to gamble. Every time he goes to the track, he flips a fair coin to determine whether to bet that day. If it comes up heads, he bets on his favorite horse, Speedy. If it comes up tails, he doesn't bet. On your way to the track today, you're 1/6 confident that out of the 6 horses running, Speedy would win. You were 50% confident that Jones' coin would come up heads. And we assume independence between the horse race and the flip of the coin. Then you see Jones leaving the track with a smile on his face. The smile tells you that either Jones bet on Speedy and won, or Jones didn't bet and Speedy didn't win. So use H and S for speedy wins and coin comes up heads, express the information you learned when you see Jones. So what you learned was H and S or not H and not S. After updating on this information by conditionalization, how confident are you that speedy won? How confident are you that the coin came up heads? Now, H and S are independent of each other, and the disjunction in the last answer is exclusive. The disjunction between H and S or not H and not S. So its value is the sum of 1 over 12 plus 5 over 12, which is 1/2. We look for the probability of S conditional on this disjunction, which by the ratio formula is the probability of S times the probability of the disjunction, all divided by the probability of the disjunction. Putting that in numbers, we get 1/6 times 1/2 over 1/2, which equals 1/6. Call this evidence E. We need to know the reverse conditional probabilities as well. What's the probability of E given H, probability of E given S, E given not H, and E given not S? It's helpful to notice that the suppositions in question, here's what I mean by suppositions. The thing that you're conditioning on. Those suppositions always rule out one of the two disjuncts of E, so that the value we seek is, for example, the probability of H and S given H, or similar items for the other cases. The result we end up with then is that the probability of E given H is 1/6, E given S is 1/2, E given not H is 1/6, and E given not S is 5/6. We then just plug those numbers into the probability calculus. The important thing is that there's a difference. One of the probabilities changes and the other one doesn't. So the probability of H given the evidence doesn't change. The probability of S given the evidence does. Why? And we're not supposed to say, because that's what the math says. All right, the reason is this. The probability of heads given the evidence is a very special case where the probability of heads is the same as the probability of not heads. You get a symmetry there that happens in only one particular value for a probability. In cases where the probabilities aren't the same, as in the speedy winning case, you have an asymmetry between the probability of S and the probability of not S, and for any other proposition you might want to pick. If the probability isn't exactly 1/2, you get different ones. And then when the probabilities are different, you're going to get a higher probability for the asymmetrical case than you will for cases where the probabilities of the event and its denial are symmetrical. So that's why the probability changes in one case but not in the other. Now to some more abstract, less number crunching kinds of things, although we have to calculate some numbers. So Jane, at 3 times, Jane assigns credences to atomic propositions P and Q. Her distributions satisfy these 6 constraints. I won't bother to read them all, but that's what we're supposed to do. We're supposed to honor the 6 constraints by constructing a credence and say what the credence distributions are for T2 and T3. And you can verify by looking at what the credences are that the credence at time 2 is certain of P and Q and of nothing else, and at time 3 equally split between not P and Q and not P and not Q, but 0 confidence in the other 2 lines of the truth table. So we should go through and make sure that those 2 things are true. So look at number 5, for example. The credence in the conditional is the same across the 2 times. So what is this? This is not P or Q. So this is the sum of lines 1, 3, and 4. And notice the sum of lines 1, 3, and 4 at time 2 are 1, and the sum of 1, 3, and 4 at time 3 are 1. So that's how you verify that condition 5 is satisfied. At time 3, she's certain of not P and Q. So that means P and Q gets a credence of 0. At time T1, she's certain that Q entails P, but we're not asked to fill in anything at that time for right now. So let's make sure that we did the credences. What's the credence for P and Q? Oh, that 3 is about time 1 as well. The credence for Q given not P is Q and not P, which is 0.5, divided by 1, which is not P, and 0.5 divided by 1 is 0.5. So that credence is honored. And all the others, we're told at 2 that she learns P and nothing else and updates, but we're not told anything. One of the reasons we put credence 2 for line 1 at 1 is it's one way of making sure that she becomes certain of P. Okay, so that's what we have as a chart for CR sub 2 and CR sub 3. Then the idea is to retrodict rather than predict and try to figure out what the credences were at, that grabs too much information. You're supposed to figure out what the credences are at time 1 that could lead you to the credence at time 2 by conditionalizing. So these are values that will do that: 2/3, 0, 1/6, and 1/6. Now, this is a crazy chart because it can't actually be a case of updating by conditionalization between times T2 and T3 because extreme probabilities can never change. So you can't go from being certain of either P or P and Q at the second time and then losing that certainty at a later time. And furthermore, if you have a credence of 0, it can't ever get moved off of that extreme value either. So extreme probabilities can never change by conditionalization, and our chart requires that. Okay, on to D. The hypothetical priors theorem says that if an agent always updates by conditionalizing, then her credences can be represented by a hypothetical prior distribution. Is the converse true? So suppose your credences can be represented by a hypothetical prior distribution. Does it follow that you always update by conditionalization? And the answer is clearly no. Start with a prior that is a probability distribution, and then do crazy shit violating the probability calculus all over the place. The priors don't rule that out. 4.8 is a bit more complicated. Suppose you have a finite partition, B1 to Bn. Suppose also that between T1 and T2, you conditionalize on evidence equivalent to a disjunction of some of the B's. Prove that for any A in the language in any compartment in the partition, such that the compartment has a non-zero probability, your later conditional probabilities are going to match your earlier ones. When we sum the conditional probability on each of the compartments times the size of the compartment, they sum to 1. That's the total probability theorem. Some of the members may not be part of the disjunction that we're talking about. You conditionalize on evidence equivalent to a disjunction of some of the B's. So carve off the ones that are relevant from the ones that aren't. So we can partition the space into a disjunction of those that are part of the disjunction and those that aren't. Those that aren't can't change their value from the first time to the second. So neither can the sum of the disjunction on which conditionalizing occurs change either, on pain of no longer summing to 1 for the entire partition. We can repeat this line of argument for any disjunction of any length all the way down to a disjunction of 2 members, but any single member of the partition is a disjunction of it or itself. So our argument generalizes to cover every single case, including a single case, so long as the conditional probabilities are defined. And that's what the greater than zero, strictly greater than zero requirement guarantees. Finally, an open-ended question at the end. Do you think only one set of ultimate evidential standards is rationally permissible? Put another way, if two agent series of credence distributions can't be represented by the same hypothetical prior distribution, must at least one of them have assigned irrational credences at some point. Now, what you say will depend on how you think about this. Some people will say, I'm a restrictivist. There's only one opinion given a body of information available. There's only one opinion you're allowed to have, and everybody has to have the same opinion if they have that same information. I don't think that's true, but that has to do with some work that I do in epistemology. So here's the answer given the kind of work that I do. I don't think restrictivism is true. There are details of my view in my book, Reflection and Rationality. Briefly, the story is this. The story about optionality here is partially a function of the role that reflection plays in the story of rationality. But there's another aspect besides reflection which triggers optionality, and that's about risk-taking people versus risk-aversive personality styles. I don't think there's one set personality style that all rational people have to have. And if one person is more risk-averse in what to make of the evidence, that person will update in ways that differ from a person who is more risk-taking. If there's optionality about appropriate levels of risk, there's going to be optionality about what opinions are required or made rational by a given body of information.